Okay, so this video is about directing groups on a benzene ring. So if you take something like phenol, for example, okay, phenol, and you add bromine, and you want to do further electrophilic substitution, so this is further electrophilic substitution. Okay, where does the bromine go? There are bromine, not bromine, sorry, the OH and NH2 are activating groups. Okay, so what I'm just going to do is going to split this in half, okay, like this. And if you take something like phenol, and if you take something like phenylamine, so the NH2 and the OH, when they're already attached to the benzene ring and you want to add another electrophile through electrophilic substitution, they are called activating groups. Okay, activating groups. The reason why they're called activating groups you don't need to know, but it's because there is a lone pair of electrons on the oxygen, there's a lone pair of electrons on the nitrogen, and the lone pair of electrons gets delocalized, gets attracted into the ring, therefore increases the pi electron density of the ring, and so making it more susceptible to electrophilic attack. Okay, so when you have already OH on the benzene ring and NH2 on the benzene ring, they're called activating groups, and they are more susceptible to electrophilic attack. Yeah, more susceptible to electrophilic attack. Whereas if you had something like NO2, like nitrobenzene, yeah, or something like a benzoic acid, they have the opposite effect. They're called deactivating groups on the benzene ring. Deactivating groups on the benzene ring. Okay, and that's, again, you don't need to know why, but it's because that they have double bonds. So carboxylic acid has double bonds within it, NO2 has double bonds within it, and it forms a conjugated system with the benzene ring. So that's like a system of connected p orbitals, and it actually takes some of the pi electron density away from the benzene ring. Okay, so they're called deactivating groups. So they are not going to react as readily with electrophilic attack. Yeah, so they are less reactive for electrophilic substitution. Yeah, so if you add phenol and bromine, this happens with bromine water, this happens at room temperature. Yeah, and it's just a very reactive reaction. Whereas if you take nitrobenzene and bromine, then you're going to need a halogen carrier, something like FeBr3. You're going to need high temperature, so they're not as reactive as the activating groups. Okay, and the other point as well is that they substitute in different positions. So if you take phenol, okay, as an activating group, and you want to put another electrophile on there, and if you number your carbons, so this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5 and carbon 6, then the activating groups, then they further substitute in the 2 position and in the 4 position. Yeah, so they are called 2,4 directing groups. Okay, there's another name for the 2 and 4 position. So the 2 is called the ortho, 3 is called meta, and 4 is called para. So you may see those terms, but for OCR, those are extension terms. Ortho, meta, para. So 2,4 directing. So if you add bromine onto phenol, then bromine can go. So you've got your phenol. And if you react it with bromine, then it could go here, or the bromine could go there, or the bromine can go there. Yeah, because remember that even though we're calling that 6, this carbon is carbon 6. If you turned it around, it could be carbon 2, 3, 4, 5, 6 as well. Yeah, so you could have forming tribromophenol. Yeah, so 2,4,6 tribromophenol. Now, if you take nitrobenzene and you do get it to react with bromine, okay, then carbon, let's just number the carbons: carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Then the nitro group will direct the bromine to go onto carbon 3. Will direct the bromine to go onto carbon 3, which is the meta position, and so it's called a 3 directing substituent. Yeah, and so if you add bromine, then the only product you will get is where it's in the 3. The bromine is in the 3 position. Okay, because it activates the that part is position 3 is the place where the bromine will go. Okay, now as a general, this is not absolute, but the 2,4 the 3 directing groups have a double bond. Yeah, so you took an NO2 COH. This is how I remember it. You're also thinking things like aldehyde, CHO, and you're thinking like esters, and you're thinking like the nitriles, CN. So if the substituent on the benzene ring has a double bond, then it is a 3 directing substituent. Whereas if the substituent on the benzene ring is an OH or NH2, or if it is an R group on there, or if it's a halogen, then it's a 2,4 directing group. Okay, now this is really important for organic synthesis. So let's just quickly see this as an example in organic synthesis. So say if you had an exam question, okay, and you were asked to convert in organic synthesis benzene, and in 2 steps you had to take benzene to this molecule here, okay, which is called, do you know what it's called? It's called 3-bromo, because we're going to go 1, 2, 3, 3-bromo nitrobenzene. I've run out of room, so I'm just going to write it underneath, nitrobenzene. Okay, now you've got 2 steps in this organic synthesis to get there. Okay, there's 2. Which electrophile do you react first? So let's say first, say if you take the pathway of adding bromine halogenation with a halogen carrier, okay, which will then give you bromobenzene. Okay, then you decide to add concentrated nitric acid and the catalyst concentrated sulfuric acid in order to at 50 degrees in order to do nitration. Where is the nitro group going to go? Well, Br is a 2,4 directing group. 2,4 directing group. Okay, so the NO2, if this is carbon 1, okay, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, then the NO2 is either going to go, let's draw the options, the NO2 will either go there, okay, or or that's the 2 position, or it could go here, squeeze it in, sorry, pardon me, squeeze it in. There's 2 options there, yeah, for nitro, for bromo nitrobenzene. Okay, but that's not what you have been asked to make. Okay, so therefore you cannot do this pathway. What you need to do is you need to do the nitration first. So if you do the nitration first and get nitrobenzene, then because nitro is a 3 directing group, substituent, and then you do the bromination, so then you do the bromine, okay, so you do the concentrated nitric acid, concentrated sulfuric acid first, okay, and then you do the bromination, so that is going to form in the 3 position, so remember 1, 2, 3, and that's where the bromine is going to go. Okay, I hope you found this helpful. Thank you.